Welcome back to the deep dive. This time we're taking you on a journey through the exciting world of quantum computational advantage. We've got a stack of research papers detailing experiments claiming to have achieved this elusive quantum supremacy. But as we'll see, it's not a simple win for quantum computers. Our goal today is to help you understand how this landscape has shifted over the years.
The pursuit of quantum computational advantage is a fascinating dance between the development of quantum hardware and classical algorithms, always pushing the boundaries of what's possible.
Exactly. To map out our deep dive, we'll focus on three main types of experiments: random circuit sampling, Gaussian boson sampling, and quantum simulation. Before we get lost in the weeds of specific experiments, though, let's make sure we're all speaking the same language. Could you clarify what quantum computational advantage truly means and why it's so significant for the field?
Quantum computational advantage signifies the ability of a quantum computer to perform a well-defined computational task demonstrably faster than is believed possible on any classical computer, even with theoretical future advancements in classical hardware. It's a high bar to clear.
So it's not just about being faster. It's about performing calculations that are thought to be impossible for classical computers, at least within practical timeframes.
Precisely. And it's important to emphasize that this advantage is highly dependent on the specific problem we're looking at. It's not a blanket statement about quantum computers being superior across the board. It's about identifying those specific areas where they can truly shine.
As we analyze these experiments, we'll encounter specific terminology used to assess the claims of quantum advantage. What's the difference between a challenge, a weak refutation, and a strong refutation?
A challenge refers to a significant improvement in the time required for classical simulation of a quantum experiment, raising questions about the initial claim of quantum advantage. A weak refutation goes further, providing evidence, usually through an improved algorithm combined with realistic projections of future classical hardware capabilities, that the quantum experiment could be matched or surpassed classically. Finally, a strong refutation occurs when a classical simulation demonstrably outperforms the quantum experiment in terms of speed, essentially invalidating the initial claim.
Okay, so a spectrum of confidence levels in these claims. With these definitions in mind, let's dive into the first category: random circuit sampling, or RCS. This is where the quantum supremacy debate truly gained momentum.
Yes, and Google's 2019 experiment with their Sycamore quantum computer is a landmark event in this journey.
It certainly grabbed everyone's attention. Can you walk us through the experiment itself? What was Google attempting to achieve?
They were tackling the problem of random circuit sampling, which involves sampling bit strings from a specially designed quantum circuit with a structure that makes it very difficult to simulate on a classical computer. Essentially, you're trying to predict the probability of observing certain outcomes from this complex quantum process.
And Sycamore itself, how big a leap was this in terms of quantum hardware?
Sycamore, with its 53 qubits, was a significant step forward in terms of scale and control. They ran this complex circuit for 20 cycles and generated 1 million samples in just 200 seconds. Based on the best classical algorithms at the time, they estimated it would take the Summit supercomputer around 10,000 years to perform the same simulation.
A 10,000-year gap certainly sounds like a strong argument for quantum supremacy. But this is where the story gets interesting, right? The classical computing community doesn't back down easily.
Absolutely. What's fascinating about this field is the rapid evolution on both sides. Google's claims sparked a flurry of activity in the classical computing world. Early challenges arose from researchers using tensor networks to simulate the quantum circuit more efficiently, chipping away at that 10,000-year estimate.
So even though Sycamore was a breakthrough, classical techniques were already evolving to narrow the gap.
Precisely. And then came a clever approach that exploited the inherent noise present in Google's quantum computer to speed up classical simulation. This highlighted the idea that the imperfections of current quantum hardware could be turned into an advantage for classical algorithms.
A clever twist. So were these challenges enough to completely refute Google's claim?
Not at that time, but the race was on. The most dramatic challenge came from Pan and Zhang's big head algorithm. This approach cleverly restructured the tensor network calculations and managed to reduce the estimated classical simulation time to just 5 days.
A dramatic improvement indeed. From 10,000 years down to 5 days. So the goalposts had shifted considerably. What happened next?
Researchers using the Sunway supercomputer in China further narrowed the gap, developing sophisticated techniques to sample bit strings even faster than Sycamore. This continuous back and forth ultimately led to a strong refutation of Google's initial claim. In 2024, Zhao et al. Demonstrated a classical simulation that outperformed Sycamore, proving that the task was no longer beyond the reach of classical computers.
This highlights an important point.
Right.
A claim of quantum advantage is never truly settled. It's a dynamic process influenced by advancements on both sides.
Exactly. And the RCS story perfectly encapsulates this dynamic. What might seem like a decisive quantum win today might be challenged or even surpassed by new classical techniques tomorrow.
A fascinating insight. Now let's move on to Gaussian boson sampling, or GBS, which utilizes a different type of quantum computer based on photons. Could you briefly explain the concept of GBS and why it's relevant in the discussion of quantum advantage?
Certainly. Gaussian boson sampling operates on a platform that utilizes photons, particles of light, rather than the superconducting qubits found in machines like Sycamore. It exploits the quantum properties of photons, specifically their tendency to interfere with each other.
Interfere. Could you expand on that a bit?
Imagine sending a boom of light through a series of beam splitters, devices that split the light into multiple paths. The photons can take different paths and, depending on the specific arrangement, interfere with each other constructively or destructively. This interference creates patterns of photon detection that are extremely difficult to calculate classically.
So it's about harnessing the inherent probabilistic nature of quantum mechanics to create a computational challenge for classical computers.
Precisely. And this is where the Jizang quantum computer from the University of Science and Technology of China, or USTC, enters the picture. They conducted several experiments aimed at showcasing quantum advantage using GBS.
What was their initial setup and claimed advantage?
Their first experiment used 50 squeezed states of light, special quantum states, with reduced uncertainty in certain properties. These squeezed states were sent through a network of 100 modes representing the possible paths for the photons. They detected up to 76 photons at the output.
And their estimated simulation time for a classical computer.
Based on their calculations, simulating this experiment on the Taihu Light supercomputer would take an astounding 2.5 billion years. This, of course, was a bold claim, even surpassing Google's initial 10,000-year estimate.
So another significant milestone in the quest for quantum advantage. But I imagine this claim, too, was met with scrutiny and challenges.
It was, and this is where we see the importance of critically examining the assumptions underlying these claims. One line of attack focused on the indistinguishability of the photons used in the experiment. The claim relied on the assumption of perfectly identical photons, which, in real-world scenarios, is difficult to achieve.
So any deviations from perfect indistinguishability could potentially make the classical simulation much easier.
Exactly, and other researchers exploited the phenomenon of photon collisions. Since Jizang used threshold detectors, which only register the presence or absence of a photon in a mode, it was argued that collisions could be leveraged to simplify the classical simulation.
So again, turning a potential weakness of the quantum experiment into an advantage for classical algorithms.
Yeah.
Did these challenges invalidate the claimed advantage of Jizang?
While not definitive refutations at the time, they certainly highlighted the need for cautious interpretation of these results. The most significant development came later with the emergence of even faster classical algorithms, again based on tensor networks. These advancements reduced the simulation time to just minutes, effectively eclipsing the claimed advantage of Jizang.
Minutes versus billions of years. A stark reminder of the constant evolution we see in this field.
Indeed. And it underscores the importance of considering not only the current capabilities of classical computers, but also their potential for rapid advancement. Before we move on to quantum simulation, are there other noteworthy experiments that don't fit neatly into the categories of RCS or GBS?
That's a great point. The pursuit of quantum advantage isn't confined to just these two approaches.
Exactly. One notable example is Xanadu's Borealis experiment, which utilizes a fully programmable Gaussian boson sampling device. This experiment involved 216 squeezed states of light and 216 modes with up to 219 detected photons. They estimated that generating even a single sample from their experiment would take a supercomputer around 9,000 years.
Fully programmable. That seems like a significant advantage over the partially programmable Jizang 2.0. Has their claim been challenged?
It has, though not definitively refuted as of yet. And we've also seen Google return to RCS with larger experiments, pushing the boundaries with 67 and 70 qubits on their improved Sycamore processor. They estimated that simulating these new experiments would take around 10,000 years on the Frontier supercomputer.
So the race in RCS continues. Did USTC also continue their work with Gaussian boson sampling?
Yes, they developed Juzong 3.0, detecting up to 255 photons, a significant increase from their previous work. Notably, they incorporated pseudo-photon number resolving detectors, which provide more information about the number of photons in each mode, making classical simulation even more challenging. These advancements, while not definitively establishing quantum advantage, illustrate the continuous progress being made in both quantum hardware and algorithmic approaches.
It seems exploring different problem types and platforms is crucial for understanding the true potential of quantum computation. It's not just about one specific algorithm or experiment, but about expanding our understanding of what these machines can achieve.
Exactly. It's about pushing the boundaries of both quantum and classical computation, exploring new frontiers, and ultimately gaining a deeper understanding of the nature of computation itself. Now, let's turn our attention to quantum simulation.
Sounds great. Let's talk about that next. So far, we focused on specific experiments and the ongoing tug-of-war between quantum and classical computing. But there's a deeper theoretical layer to all of this, isn't there? What makes certain problems difficult for classical computers, yet potentially solvable by quantum computers? What are those fundamental differences that give quantum computers their edge?
At the heart of quantum computation lies a set of principles that deviate dramatically from classical computing. One of the most important is quantum superposition. Unlike a classical bit, which can exist in only one state, either 0 or 1, a qubit can exist in a superposition of both states simultaneously.
So instead of being a definite 0 or 1, it's in a state that encapsulates both possibilities. And this is what gives quantum computers their inherent parallelism.
Precisely. This ability to explore multiple possibilities at once is one of the core advantages of quantum computation. Another key concept is quantum entanglement, where two or more qubits become correlated in a way that has no classical analog. This allows for operations on multiple qubits simultaneously, further enhancing the computational potential.
Entanglement is often described as spooky action at a distance, a rather apt description given its strange nature. Are there other key elements that contribute to this quantum advantage?
Quantum interference is another crucial concept. Just as waves can interfere with each other, so too can quantum states. This interference can be carefully controlled to amplify desired outcomes and suppress unwanted ones, allowing for precise manipulation of quantum information. These core concepts, superposition, entanglement, and interference, form the foundation of quantum algorithms, enabling them to tackle certain problems in ways that are fundamentally different from classical approaches.
So quantum computers aren't simply faster versions of classical computers. They operate on entirely different principles, opening up new avenues for solving problems that were previously intractable. However, we've also seen that realizing this advantage in practice is a formidable challenge.
Of course. One of the most persistent challenges is noise arising from the interaction of quantum systems with their environment. Any such interaction can introduce errors that corrupt the computation, requiring robust error correction methods for reliable operation.
This brings us back to the importance of fault tolerance, which we discussed earlier. But even if we manage to build stable and reliable quantum computers, there's still the question of identifying the problems where a quantum advantage is most likely to exist. How do theorists approach this challenge? What are they looking for?
One approach is to focus on problems where classical algorithms are known to be inefficient or even intractable, such as problems classified as NP-hard. These problems are characterized by the exponential growth in computational resources required as the input size increases, making them incredibly challenging for classical computers to solve, especially for large instances.
So it's about finding problems where classical computers hit their limits and exploring whether quantum algorithms might offer a more efficient solution.
Exactly. Another strategy is to identify problems with inherent quantum structure, meaning problems that can be naturally mapped onto the language and principles of quantum mechanics. These often involve simulating quantum systems themselves, such as the behavior of molecules in quantum chemistry.
So it's a dual approach, finding problems where classical computers falter and problems that naturally lend themselves to quantum solutions. And once a promising problem is identified, the next step is to design a quantum algorithm that exploits these quantum advantages.
Precisely. This is where the ingenuity of quantum algorithm designers comes in. Designing effective quantum algorithms requires a deep understanding of both quantum mechanics and computer science. It's not simply about writing code, but about harnessing the power of quantum phenomena to create new computational pathways.
It's fascinating how these algorithms weave together complex mathematical concepts and the unique features of quantum mechanics to solve computational challenges. But even with a promising algorithm in hand, there's still the rigorous task of proving that it actually offers a quantum advantage.
Yes, this involves rigorous mathematical analysis and comparison with the best-known classical algorithms. This process is often an iterative back and forth between quantum algorithm designers and classical algorithm experts, each pushing the boundaries of their respective fields. This constant competition is crucial for driving innovation and progress in both areas.
It's like a constant game of one-upmanship, pushing both sides to innovate and explore new approaches. Earlier, we briefly touched on quantum phase estimation. Can you elaborate on this algorithm and its potential?
Quantum phase estimation, or QPE, is a fundamental algorithm in quantum computing. Its goal is to estimate the eigenvalue of a unitary operator.
Eigenvalue. Unitary operator. Could you unpack those terms for us?
Certainly. Imagine a quantum system evolving over time. The unitary operator describes the transformation of the system as it evolves. The eigenvalue associated with that operator represents a specific numerical value related to the evolution. This could be a physical quantity such as energy or frequency.
So it's like characterizing the fundamental properties of the system's evolution, and QPE provides a way to extract these values with high precision.
Precisely. This information is crucial for understanding the system under investigation. For instance, in quantum chemistry, the eigenvalue might represent the energy level of a molecule, while in cryptography it could be linked to the period of a function used in encryption.
So QPE has the potential to impact a variety of fields, from simulating molecules to cracking codes. But we also discussed how its advantage in quantum chemistry is still debated.
Yes, the theoretical speedup offered by QPE is clear. But in practice, noise and limitations in current quantum hardware pose significant challenges, particularly for large and complex molecules. Achieving practical quantum advantage in quantum chemistry remains an active area of research, pushing both theoretical and experimental boundaries.
So it's a reminder that bridging the gap between theoretical potential and practical implementation is crucial in this field. It's not just about developing algorithms, but about developing algorithms that can function effectively on real-world quantum devices.
Absolutely. And while we strive to unlock the power of quantum computers, it's also important to understand their limitations. It's a common misconception that quantum computers are inherently superior to classical computers for all tasks. There are inherent limitations to what they can do.
That's an interesting point. So it's not a case of quantum computers replacing classical computers entirely, but rather a matter of identifying the specific domains where they can excel.
Precisely. And theoretical research plays a crucial role in understanding those limitations. For example, there's a class of problems known as BQP-complete. These problems are believed to be the hardest problems that can be efficiently solved by a quantum computer in polynomial time, meaning the time it takes to solve them grows at a manageable rate as the problem size increases.
So even for quantum computers, these problems are likely to remain challenging. It emphasizes that while quantum computers hold tremendous promise, they are not a magical solution to every computational problem.
Exactly. Understanding the boundaries of quantum computation is crucial for directing research efforts and setting realistic expectations. This leads us to the question of exploring different models of quantum computation.
Right. We've been mainly discussing the gate-based model. What are some of the alternative models being explored, and how do they differ from the gate-based approach?
Yeah. The gate-based model, where computations are performed by applying sequences of quantum gates to qubits, is the most widely studied model. However, there are other approaches. One is adiabatic quantum computing, which is the method used by D-Wave's quantum annealers.
Right, those were mentioned earlier. Could you elaborate on how adiabatic quantum computing works?
In adiabatic quantum computing, you start with a system in its ground state, which is its lowest energy state. Then you slowly change a parameter of the system known as the Hamiltonian over time. This Hamiltonian describes the system's energy, and the goal is to evolve the system in a way that keeps it in its ground state throughout the process.
So instead of actively manipulating the system with gates, you're carefully guiding it towards a desired solution by manipulating its energy landscape.
Precisely. If the final Hamiltonian is designed to represent the solution to a specific problem, the system's evolution naturally leads it towards that solution. This approach is particularly well suited for certain types of optimization problems.
So it's a fundamentally different approach compared to the gate-based model. Instead of applying discrete operations, you're letting the system evolve under carefully controlled conditions.
Are there other alternative models being investigated?
Yes. Another model gaining traction is measurement-based quantum computing.
Measurement-based. That sounds intriguing.
In this model, computation is performed by making a series of measurements on a highly entangled state of qubits. The choice and order of measurements determine the computation being performed. Essentially, you're extracting information through the act of measurement.
So it's a different way of harnessing the power of entanglement for computation. And it's not just about exploring new models of computation, but also about identifying the types of problems where quantum computers might have a practical advantage.
Absolutely. And this leads us to the fascinating and sometimes controversial role of sampling problems in the quantum advantage debate. We've already seen examples of this with random circuit sampling and Gaussian boson sampling. Right, those experiments generated a lot of buzz. Why are sampling problems considered such a significant testing ground for quantum advantage?
Sampling problems involve generating samples from a probability distribution. Certain quantum algorithms have shown the potential to perform this task more efficiently than classical algorithms. They've become a focal point because they provide a clear-cut way to compare the capabilities of quantum and classical computers.
But, as we've seen, those claims of advantage in sampling haven't been without their skeptics. Some argue that while sampling problems are theoretically interesting, they might not have immediate practical applications. What are your thoughts on this?
It's true that the practical relevance of sampling problems has been a topic of debate. However, even seemingly esoteric problems can lead to unexpected applications down the line. Dismissing them entirely would be premature.
So it's a matter of keeping an open mind and exploring the full spectrum of possibilities.
Precisely. It's about understanding that scientific progress often follows unpredictable paths. What might seem purely theoretical today could lay the foundation for groundbreaking applications tomorrow.
That's a great perspective. Now, you mentioned potential applications in quantum machine learning. Could you elaborate on that?
Quantum machine learning is a burgeoning field exploring the potential of quantum computers to enhance or even revolutionize machine learning algorithms. Sampling plays a central role in many machine learning techniques, and quantum computers might offer a significant speedup in generating samples from complex probability distributions, leading to faster and more powerful algorithms.
So, while the immediate applications of sampling problems might not be apparent, their role in shaping the future of quantum machine learning could be profound.
Absolutely. And the exploration of quantum advantage goes beyond just scientific and technological advancements. It has significant implications for various industries and society as a whole.
Right. We can't ignore the potential impact on areas like cybersecurity, medicine, material science, and even finance. If quantum computers achieve a decisive advantage, the consequences could be far-reaching.
Exactly. One area where the impact is likely to be significant is cryptography. As we discussed earlier, Shor's algorithm, if implemented on a powerful enough quantum computer, could threaten the security of widely used encryption methods.
That's a serious concern. Many of our digital infrastructures rely on the difficulty of factoring large numbers, and Shor's algorithm offers a way to crack that code.
It does, and this potential threat has spurred research into post-quantum cryptography encryption methods designed to be resistant to attacks from quantum computers. It's a race against time to develop and deploy these new methods before quantum computers become powerful enough to break existing ones.
So it's a critical challenge for the cybersecurity community.
It is. However, it's important to remember that quantum computers could also contribute to advancements in cryptography. For instance, quantum key distribution, or QKD, exploits quantum principles to enable secure key sharing between parties, potentially enhancing security in a post-quantum world.
So it's a two-sided coin. Quantum computers could both threaten existing encryption methods and pave the way for new, more secure ones.
Precisely. And the impact extends beyond cryptography. In drug discovery, quantum computers could revolutionize the process by enabling the simulation of molecules and chemical reactions with unprecedented detail. This could lead to the design of more effective drugs with fewer side effects.
So instead of relying on lengthy and costly trial and error processes, we could use quantum simulations to guide drug development, significantly accelerating the pace of discovery.
Exactly. And the same principle applies to material science. Quantum simulations could enable the design of materials with specific properties, leading to breakthroughs in energy storage, electronics, and manufacturing. The potential applications of quantum advantage are vast and could reshape numerous industries.
It sounds like we're on the cusp of a new technological era, driven by the power of quantum computation. However, it's crucial to maintain a balanced perspective. We're still in the early stages of development, and realizing the full potential of quantum advantage requires continued progress on multiple fronts.
Absolutely. Building large-scale, fault-tolerant quantum computers remains a formidable challenge. Equally important is the development of efficient and robust quantum algorithms capable of tackling real-world problems.
So it's not just about the hardware, but also about the software that runs on these machines.
Exactly. Advancing this field will require collaboration between researchers, industry partners, and policymakers to navigate the scientific, technological, ethical, and societal implications of these advancements.
So it's a multifaceted challenge, requiring expertise from various fields.
It is, but I believe the potential benefits of quantum advantage are so significant that the effort is well worth it. The potential to unlock new scientific discoveries, develop revolutionary technologies, and address some of humanity's most pressing challenges is truly exciting.
I agree. It's a journey filled with challenges, but the potential rewards are immense. And it's a journey that's just beginning. We've covered a lot of ground in our exploration of quantum computational advantage, from the theoretical underpinnings to the experimental breakthroughs and the ongoing race between quantum and classical computing. It's clear that this field is dynamic, full of both promise and challenges. Now, let's turn our attention to the future. What might the road to achieving a decisive and lasting quantum advantage look like?
It's an exciting question, and one that occupies the minds of researchers worldwide. While we've seen glimpses of quantum advantage in specific tasks, achieving a broad and undeniable advantage, one that consistently surpasses classical capabilities will require continued progress on several fronts.
So far, the advantages we've discussed seem to be temporary, with classical algorithms often catching up or even surpassing quantum computers on those specific tasks. What needs to change for quantum computers to pull ahead in a more substantial and enduring way?
One crucial area is the development of more robust and scalable quantum hardware. Noise and errors have been persistent obstacles, limiting the complexity and reliability of quantum computations. We need quantum computers with significantly lower error rates, longer coherence times, and higher qubit connectivity.
You mentioned coherence time earlier, but could you remind us why it's so crucial?
Coherence time refers to how long a qubit can maintain its quantum state before it's disrupted by interactions with its environment, leading to errors. It's essentially the lifespan of the quantum information encoded in the qubit. Longer coherence times are essential for performing more complex and intricate quantum computations.
So it's about extending the window of opportunity for manipulating and processing quantum information. And
Yeah.
what about qubit connectivity? Why is that important for achieving quantum advantage?
Higher qubit connectivity allows qubits to interact with each other more efficiently, enabling the implementation of more complex quantum algorithms. Imagine a network where the nodes represent qubits and the connections represent their ability to interact. The richer and more interconnected this network, the more sophisticated the computations it can perform.
So it's about creating a quantum computing architecture that allows for complex interactions and information flow between qubits.
Precisely. And alongside hardware advancements, we need progress in developing more sophisticated quantum algorithms. Even with more powerful hardware, we still need algorithms specifically designed to exploit the unique features of quantum computers.
So it's not just about having better machines, but about having the right software to run on those machines. What characteristics should these future algorithms possess?
They need to be more efficient and robust, capable of tolerating the noise and errors that are inherent in current quantum devices. Fault tolerance is a key consideration. We also need algorithms that go beyond the existing paradigms, algorithms that can truly unlock the power of quantum computers for tasks that are intractable for classical computers.
So algorithms that push the boundaries of what we currently believe is possible with quantum computation.
Exactly. We need algorithms capable of tackling complex problems in areas like optimization, machine learning, and simulation, problems that remain beyond the reach of even the most powerful classical supercomputers.
You've painted a compelling picture of what needs to happen for quantum advantage to truly blossom. What are some specific areas of research and development that you find particularly exciting and hold the potential for significant breakthroughs?
One area that holds immense promise is quantum machine learning, which we've touched on throughout our discussion. Quantum computers have the potential to revolutionize machine learning by speeding up tasks like pattern recognition, classification, and optimization, leading to faster and more accurate models.
So it's not just about developing new quantum machine learning algorithms, but also about leveraging quantum techniques to enhance existing classical algorithms.
Precisely. We can think of it as a hybrid approach, combining the best of both worlds to push the boundaries of machine learning. Another area where I see significant potential is materials science. Quantum computers could enable us to simulate the behavior of molecules and materials at a level of detail that's simply impossible with classical computers.
This could revolutionize our understanding of how materials work at the atomic and molecular level, leading to the design of new materials with tailored properties.
Exactly. Imagine being able to design materials with specific properties such as superconductivity, high strength, or unique optical or electronic characteristics. This could have profound implications for industries ranging from energy to electronics to manufacturing.
It sounds like quantum advantage could usher in a new era of materials discovery driven by our ability to precisely model and manipulate matter at its most fundamental level.
And it doesn't stop there. The potential applications extend to fields like drug discovery, where quantum simulations could accelerate the process of designing and testing new drugs, financial modeling, where quantum algorithms could provide a competitive edge in complex market predictions, and even weather forecasting, where quantum computers could enhance our ability to model and predict complex weather patterns.
It's truly a wide-ranging landscape of possibilities with quantum advantage potentially impacting almost every aspect of our lives. However, amidst all this excitement, it's important to acknowledge that significant challenges lie ahead.
Of course. Building large-scale, fault-tolerant quantum computers is a monumental engineering and scientific challenge, and developing the algorithms that will unlock their full potential is an equally demanding intellectual endeavor.
So it's a multifaceted effort requiring sustained investment, collaboration across disciplines, and a long-term vision.
It is, but I'm optimistic. The potential benefits of quantum advantage are so profound, the potential to advance science, technology, and society so significant that the journey is well worth undertaking.
It's been a fascinating exploration of quantum computational advantage. We've traversed the theoretical landscape, delved into experimental breakthroughs, and glimpsed the potential this field holds for transforming various industries. What key takeaways would you leave our listeners with as they continue to follow this rapidly evolving field?
I would emphasize that quantum computational advantage is not a single event, a finish line to be crossed. It's an ongoing journey, a continuous process of exploration and discovery. We're witnessing a dynamic interplay between quantum and classical computing, each pushing the boundaries of the other. And while the ultimate realization of broad quantum advantage might be years or even decades away, the progress being made is remarkable and the future incredibly exciting.
It's a field brimming with possibilities, and we've only just begun to scratch the surface of what quantum computers might achieve. We encourage our listeners to stay curious, stay engaged, and keep exploring this fascinating frontier of computation. Thanks for joining us on the Deep Dive. Until next time.